Hi everyone, we are Group 47 and today we are excited to present our analysis of foundational conference paper in field of stroke rehabilitation. The paper is titled Development of Low-Cost Virtual Reality Based Smart Glove for Rehabilitation. My name is Hashish Chitruan and I am joined my team members Malik, Monilka and Yenshi. The paper we chose was presented at 9th International Conference on Disability, Virtual Reality and Associate Technologies back in September 2012. The research was conducted by the team of Northeastern University, including authors like Ms. M. Sivak and C. Mohandis. At the time of its publication, it already had 10 citations, and its influence has only grown since, showing just how important this was. So, why this research matters? The motivation is a powerful one. Stroke is devastating event that leaves millions of people with long-term weaknesses in their hands, arms, and whole body. In fact, up to 75 of survivors still have impaired functions 6 months after their stroke. So, while rehabilitation helps, it faces huge challenges. Costs, accessing long term specialized care is expensive and limited resources, etc. So, this paper addresses that gaps, asking a crucial question, and they created a low cost in home system using virtual reality to make the rehabilitation more accessible and motivation for everybody.
Thank you, Hashi. So, to tackle the challenges of cost and access, researchers from Northeastern University developed this, the Atlas Bimanual Glove System. The name bimanual is important as it was designed to be used on both hands, which not many systems at the time were capable of. As you can see from the image, this is a comprehensive hardware prototype. It's not just a glove, it's a full system with four key components working together. First, the gloves themselves, which have the sensors embedded in them. Second, the IMUs, which are in those small enclosures that mount on the back of the hand to track orientation. Third, the resting base for hands. This piece is clever. It serves to standardize the patient's starting position for exercises and just as importantly to re-zero the IMUs before each trial, ensuring accuracy. And finally, central electronics unit, which act as the brain. It gathers the data from the glove and IMUs and combines it and send it all to a computer through a single USB connection. This also means the whole system is powered by USB, making it portable and easy to set up with any laptop. The most impressive part? The primary goal was to make it incredibly affordable, targeting a price of just $150 per glove, which was revolutionary for making this technology accessible for in-home use. Let's deep dive into technology that makes this system work. To measure finger movements, they used potentiometer-based sensors to precisely measure joint angles. This is different approach from our project which uses FSR sensors to measure force. The way they mounted these bend sensors is quite smart. They run in sleeves on the back or the dorsal side of the fingers. These sleeves allow the sensors to slide to accommodate the natural change in skin length when the finger bends, and critically they prevent the sensors from buckling upwards when the fingers extend. This design feature was crucial for improving the fidelity of the motion tracking. To track how the hand was oriented in space, it yaw, pitch, and roll, they used degree of freedom IMUs. Each contains a 3-axis accelerometer and magnetometer, allowing for robust calculation of orientation. However, they hit a significant roadblock. While the IMUs were great for orientation, the authors clearly significant that when they attempt to measure the hand's actual position in a room, the measures were not sufficiently accurate. This is a key limitation that we'll come back to later. So, with this new hardware, the researchers had a very clear and fundamental objective. They needed to assess the accuracy of their sensors. Before building complex games, they had to answer the question, is the data coming from this low-cost cloud reliable enough for a clinical rehabilitation? To find out, they designed a two-part methodology. First, they perform mechanical testing, putting the sensors on custom-built motorized rigs to check for a signal consistency over long period. This confirmed the hardware worked as expected in a controlled environment. Then they move on to the most critical part, human subject testing. They used 20 healthy people to see how the sensors performed in real world. Specifically, they wanted to see how the sensor's voltage output mapped onto actual measured hand movement and, importantly, how that mapping was affected by different hand sizes. The ultimate goal of this was to gather the data needed to one day create a calibration algorithm for the system. To explain exactly how conducted this human test and what they discovered, I'll pass over to you.
The human testing was meticulous. For the bend sensor protocol, they had 24 subjects place their hands on templates that were set to specific angles like 45 and 90 degrees. They then measured the angle with a traditional medical goniometer and compared it directly to the voltage reading from the golf sensors. For the IMU protocol, subjects would perform specific time movements like flexion and rotation, allowing the researchers to measure the accuracy of the orientation data. So, what did they find? The results were mixed but very informative. The good news was that the bend sensors were highly accurate when measuring larger finger angles. However, they discovered a challenge. The sensor's electrical response was very low at small angles, making it hard to track subtle initial movements. They also found the sensor's response was exponential, not linear, meaning a simple one-to-one mapping was not possible without a more complex algorithm. The IMU results were much more clear-cut. For measuring hand orientation, the yaw, pitch and roll the system was definite success. The data charts in the paper shows incredibly consistent and reliable tracking across all subjects as they rotated their hands and wrists. But as Monilka mentioned, for tracking the hands position in space, it was a failure. The paper is very direct about this, stating the measure was not sufficiently accurate and that an alternate solution was needed. So this is the crucial funding of our works. Finally, while the VR software was still in development, the authors shared their design concept. They planned to test two modes. The first was direct mapping, where a virtual hand on screen perfectly mimics the user's hand. The second was indirect mapping, where the user's movement would control something more abstract and fun, like the penguin you see here, to potentially boost motivation. Now, to wrap up the conclusions and connect this all back to our own project.
So, to summarize the paper, the Atlas Glove was a successful low cost prototype that proved capable of accurately measuring the hand orientation and large finger movements. Its main challenges were measuring small angles and its inability to track the hand position. The authors' planned future works was therefore very clear. They need to refine their electronics, develop a calibration algorithm for different hand sizes, and most importantly, find an entirely new way to track the hand position in space. This is where this paper becomes so valuable for our own project. It lays the perfect foundation and highlights a problem that we believe we can solve. Like the Atlas system, our project is also a low-cost smart glove for hospital use. But we are building on their work with modern technology. First, where they measure the angle with bend sensors. Our project uses FSR sensors to measure the grip force, a different but critical metric for recovery. Second, and most importantly, we directly address the key limitation they identified. Their IMUs fail to track the hand position. Our project solved this by using markerless hand tracking via a smartphone camera and a media pipe, an accessible and accurate solution they didn't have in 2012. Finally, we are introducing a layer of AI-driven personalization with our level recommendation engine, which adapts therapy to patients' real-time performance. This ensures the therapy is not just engaging but also intelligent. In conclusion, this paper was pioneering effort that paved the way for systems like ours. By understanding its successes and more importantly challenges, we have been able to design a next generation system that addresses modern AI and computer vision to create a more effective and accessible tool for stroke survivors. Thank you for your attention.